The following talk was delivered originally at Google Cloud Next 2024 in Las Vegas. Today I wanted to talk to you about modernizing consumer devices with Google Cloud, and specifically dive into MosquitoMax's story and how they got smart. One thing I'll point out though is that this isn't just for MosquitoMax. They're a local Houston company I'll tell you more about, but this applies to any company with an industrial or manufacturing process. Anything that has IoT sensors, so this could be consumer devices, it could be a more industrial or enterprise use case as well. My name is Daniel Watrous. I'm an enterprise customer engineer with Google Cloud. I have a degree in electrical engineering, and my enterprise focus at Google has allowed me to work with some of the most interesting companies in manufacturing, retail, and beyond. But this story is about a small Houston-based company with no IT staff, no engineering organization, but with an oversized ambition to get people outside to enjoy their yards. So I'm going to start off by giving you some background and explain the initial state and the desired end state of the Mister system. Then I'm going to review the solution we came up with and talk through the architectures, as well as some of the prototypes, showing you both the good and the challenges that we encountered. Finally, I'm going to show you some demos and anticipated business impact from this project. Who is MosquitoMax? MosquitoMax has been eliminating mosquitoes since 2005. They have proven and patented technology to eradicate mosquitoes. In the top left image, you see one of the nozzles spraying the chemical solution. These nozzles are usually mounted on the eaves of the house and along the fence lines. The lower picture shows one of their space-efficient tankless systems, which mixes a precise amount of concentrated chemical with water as it sprays. So what was the initial state of the Mister and controller? First of all, a Mister, in order to function properly, needs to ensure there's enough chemical and that that chemical is mixed at the appropriate ratio to kill the mosquitoes. You need to make sure that there's water coming in and unbroken line and working nozzles going out. So this makes sure that the solution mixture is correct, the timing's correct, and everything else, so that all of that is delivered to the yard as a mist. And finally, their current solution required a technician to be on site to be able to check those chemicals, the valves, the mix ratio, and so on. So the good, they had excellent and reliable tankless misting technology. They had programmable sprays, a short-range wireless remote. It was DIY friendly with an extensive YouTube library of support. There were challenges, however, one of which was that their technology is based on an obsolete rabbit controller with limited avenues to get stock. Legacy code had bugs, and there was no one to update or evolve it. It hadn't been updated in more than 6 years. And a technician had to be physically present to determine system health and status. And there was no smartphone app or weather or seasonal adjustments. So what was the business and customer impact to some of these challenges? One is that non-functional systems could go undetected for weeks or longer. That meant more mosquitoes for the customer and a loss of revenue for MosquitoMax. So what was the desired end state of the Mister controller? First of all, they wanted to lower overall costs. They also wanted to improve customer satisfaction and arrive at a point where they could use data-driven forecasting and business intelligence. In order to accomplish the desired impact, the device needed to be online and real-time. This meant achieving a real-time view of Mister status across the entire fleet, each spray producing a trove of data indicating system health and customer usage patterns. It would also require a cloud backend and a mobile app to improve the customer experience. This makes it possible to send a technician only when needed and as soon as needed. It also makes it possible to automate weather and seasonal adjustments for maximum efficiency. Let's dive into the solution. First of all, we started with the user. Specifically, we knew the user experience needed to be app-focused. Customers today expect everything to be smart, on their phone, and always available. So what were the architecture objectives? First of all, from a business perspective, you wanted to be able to monitor the entire fleet for low chemical solution, no water pressure, non-functional Mister line or nozzles, improper solution mix ratio, no power, and other possible issues. Customers should be able to schedule sprays, spray right now, skip a future spray, see when the last spray happened and when the next spray will happen. They should be able to see details about each spray and request support and manage their account, and they should be able to do all of this from their mobile device. So let's look at the architectural approach. To begin with, we knew we had to add some new equipment. We added electronic pressure sensors for the line in and the line out. We added an electronic vacuum sensor that's part of the mechanism that draws the chemical in. We added a scale to measure how much solution was remaining, and controllable relays for the valves and the pump motor. In order to read the scale, the vacuum, and pressure sensors, we added an analog to digital converter and an HX711. We chose Raspberry Pi as the microprocessor, due in part to its Wi-Fi connectivity, and a cloud backend with a mobile app and a plan to retrofit the existing fleet. The technology choices include Google Cloud, so we're using cloud storage, cloud functions, cloud run, and cloud build. Firebase, including Firestore, real-time database, auth, and messaging, and we're using Google Cloud source repositories to maintain our source code and documentation. From a languages perspective, the controller and a number of APIs are written in Python. For the mobile app in Flutter, we used Dart, JavaScript for some of the cloud functions, and Bash extensively for automation and service management on device. For the mobile app, we chose Flutter, which would give us a native Android and iOS app as well as a web interface, and we used flutterflow.io for rapid prototyping. From a hardware perspective, we settled on the Raspberry Pi Zero 2W with a custom printed circuit board. We can look at this a little differently to think about how these technology choices were made. For example, we looked at the stakeholders and the users that were involved in all of the business processes as well as the use of the machine. So from procurement to manufacturing to installation, we also wanted to think about long-term maintenance. From a back office perspective, how did the business run? What was the service offering that was being part of this? So the managed service, how would that be administered? We knew that in order to authenticate securely against the cloud backend and with the app, both the device and the consumer had to have their own authentication accounts. And then from the perspective of the development, we knew that from a controller dev perspective and an app dev perspective, we needed a cohesive solution that, one, would provide continuity from one technology to another as we delivered this. But two, it needed to be managed services. In other words, MosquitoMax being such a small company, they don't have IT staff, and it wasn't reasonable to have them setting up, maintaining, patching, and monitoring servers. So you'll see that with Cloud Build, Cloud Functions, Cloud Run, and so on, all of these are serverless solutions to ensure reliability without requiring the hiring of IT staff to constantly monitor. Another interesting point is that throughout the project for development of the controller or the app itself, Gemini was a fantastic resource. This provided code assistance, integration ideas, and best practices and patterns around the design of the overall ecosystem. Let's have a look at some prototypes. A quick look at the development timeline shows that the first working prototype of the basic cloud backend was done in January of 23. After a 6-month or so break, development picked up again, and the first PCB based on the prototype was delivered. By October, the first mobile app was delivered, and by December of 23, a working PCB with an app was available. As of February of this year, 3 complete devices are set up and running continuously. The first working prototype made use of off-the-shelf components wired together on a breadboard. This included an ADC to read pressure and vacuum sensors, and the HX711 for the load cell of the scale, controllable relays for the valves, pump motor, and the Raspberry Pi running a Python-based controller. We've been through 5 generations on the PCB, each one fixing some problems and adding new functionality. This was definitely a learning journey, For example, the first PCB arrived with male instead of female headers, which made it impossible to plug the Raspberry Pi in. There were issues with the relay circuitry, which was fixed only to have an incorrect footing that reversed the normally open to normally closed. The first functional board, Gen 3, failed to support the current requirements of the motor and burned up the trace, as you can see in the bottom right image. To keep costs low, we found a gig on Fiverr to do the design of the PCB, and we ordered the boards online through JLC PCB. In spite of some of the missteps, this approach of using a Fiverr gig and online PCB manufacturing resulted in a total cost for all 5 generations of boards of less than $1,000. That low price point makes this the lowest cost research and development project I've ever led. The first installed prototype has been running for months, including during a freeze and some other heavy weather events. The freeze made it obvious that some winterization protocols would be needed to protect the sensors. For example, you can see in the bottom right there, the vacuum sensor broke, allowing fluid to seep up through the sensor into the electronics. Warmer weather and spillover solution made it clear that the plastic scale would not hold up. You can see the bent plastic in the bottom left, preventing the load cell from reading the full weight accurately. But with iterative design and a few trips to Home Depot, we found a path forward. You can see that some metal junction box covers were used with the load cell to provide a more sturdy platform for the scale. And we also started to introduce some modifications to the original enclosure and introduce plug-and-play connectors rather than the screw connectors. All right, let's have a look at some of the demos. The demos are organized into the different stages of the device lifecycle, starting with manufacturing and going through consumer install and ongoing use. Along the top, you can see the device manufacturing starts with a blank SD card and an unboxed Raspberry Pi. Automation makes it possible to create an image for the Pi and write it to the SD card. The SD card is then added to the PCB. When first powered on, the device automatically connects to the manufacturing Wi-Fi, at which point it's ready to register. Registration operates against an API that is containerized and hosted on Cloud Run. After registration, the PCB can be assembled into an enclosure and all the sensors, valves, and motor attached. It can then be calibrated and diagnostics run to confirm expected functionality of all components. The last step is to clean the device of any sensitive data, such as the manufacturing Wi-Fi credentials. The consumer flow has the user place the device into a sort of pairing mode. The app can then connect to the device and use an onboard API to provide Wi-Fi credentials and the ID of the device owner. This allows the device to connect to the internet through the consumer Wi-Fi and associate the device with the user. Once connected, the device and app then communicate via a messaging protocol, which will also be demoed. So in the device registration flow, we're going to focus on this first part where we initially power on and the device connects to the manufacturing Wi-Fi, and then we use the control command line interface to register the device against the Cloud Run based API. In the top right, you can see I'm showing Firestore, where we'll see a new document upon registration. In the bottom, we see Firebase authentication, where we'll see a new user account for the device. And in the top left, you'll see what we're actually doing on device during this registration step. So control is the command line interface that was created for all of the onboard functionality that needed to be done during manufacturing. So here I am showing you that it's version 0.1.67 and control-h prints out a help command. One thing you'll notice is that there is no option for a -R or -- register. That actually is part of the command line interface, but it's not published, so it's a hidden menu option. We'll also have a brief look at config.js, and you'll notice that the password field is empty. So at this point, we're ready to do control -- register, which will tell the device through the manufacturing Wi-Fi to connect to the API endpoint and register this device. Registration is based on the serial number of the Raspberry Pi that is connected to the device. And what you'll see is as registration progresses, in the top right in Firestore, you'll see a new document appear that is for this specific Raspberry Pi and device, so this specific MiSTer device. And then once registration completes, if you look at that document in Firestore, you'll see that it is already pre-configured with all of the anticipated defaults. And in the bottom, we'll see that there's also a new authentication account for this new device. Now, if we take another look at the config.json in the top left, you'll see that there is also now a password field. So the specific username and password are unique to that Raspberry Pi MiSTer system and will ensure that that device can only communicate with the cloud backend for things related to that one device. Now let's look at how to calibrate a device. So keep in mind that we're at this point in the manufacturing process, Control-C is for calibrate, -D is for diagnostics. Let's start by having a closer look at the system and how it works. To start with, there are 4 built-in sensors: the scale, a vacuum sensor, and 2 pressure sensors. There are also 2 valves, one for chemical, one for water, and a motor that are being controlled. During normal operation, the chemical solution will be pulled in from the jug on the scale, and water will be pulled in from the water supply. These are mixed together and then distributed out to the individual nozzles. So here in the top left, we're going to be following the config.json file, and you'll notice that there are a number of offset values that are all 0. And in the top right, we're going to be running the control commands. So again, control-h shows the options. -C or --calibrate is our calibration option. And you'll notice that we can calibrate individually, each sensor individually, or we can calibrate them all at the same time. In this case, we're going to calibrate all of them, which will go through one by one and choose their 0. So this is effectively the same as tearing a scale. And what I want you to do is look in the top left and see that all of the offsets are now set to values that represent a 0 for that specific sensor. To go a little deeper on this, every physical sensor is going to read a little differently, and the analog to digital converter is simply converting an analog signal that it's reading, a resistance perhaps, to a number. So the offsets are saying that at rest, with no weight on the scale, with no pressure on the pressure sensor, these are the readings. Okay, device diagnostics. Let's have a closer look at diagnostics now. So diagnostics, we want to test each of the individual sensors to make sure they're working. In our command line interface, there's a -D or --diagnostics option, which when we run, the first thing that's tested is the buzzer. Next, you'll see that it's going through and showing you the LED patterns. So it's showing LED ready right now. It's switched to LED error. And by the way, the little hand that you see in there is my 12-year-old son, Henry, who agreed to help me record this demo. After it goes through all of the LED settings, then it's going to start producing an output of 7 lines, and it's going to repeat these over and over again. So the top 2, line in pressure, line out pressure, are measuring the current pressure on the sensors. And you'll notice that they're both about 14.6. The reason for that is that air pressure in Earth's atmosphere is 14.6. So we would expect 0 to be 14.6 psi. The vacuum sensor is at 0, the weight is at 0, and then there are 2 buttons, not strictly sensors, but the reset button and a float switch, which I'm using just a toggle switch for in this demo. And to be clear, the float switch, when it's engaged, when it's connected, that means that the water is full. And so the float signal would be false, meaning the float signal didn't get tripped. And if the water level in the mister ever drops to the point where the float signal is broken, the float switch will go to 0, but the float signal needs to toggle to true. So the first thing we want to do is put a weight on the scale. So we've got a little about 13-ounce speaker, and then Henry's going to push the reset button. So you'll see the reset button went from 0 to 1, and the weight shows now 13.8 ounces. When he releases the reset switch, we'll expect that to go to 0, and now he's toggled the float switch. And so we see that the reset button is back to 0, and the float switch is 0, which means the float signal is true. Okay, and then finally we're going to remove the weight from the scale, which will show us that the weight now goes back to measuring 0. So we could do something similar for the vacuum and pressure sensors as well, if we wanted to. But the point is that diagnostics gives us an opportunity to check and make sure that everything on board is working as expected. This demo shows how a user would go through adding a new device. So this starts with the app. You can see here in the bottom right that I've highlighted the little plus button. In practice, most consumers will only have one device, but there are cases where they have two or more. So when the user presses the plus button, it says, turn your device on and wait for the LED to turn white. So here we're showing that. When you click next, it says, now start pairing mode by pressing and holding the reset button until the LED starts flashing blue. And so here I am holding this. It takes about 7 to 10 seconds before the device goes into a pairing mode. But now that the LED is flashing blue, you'll see a couple of interesting things happened. One is that the device itself is now hosting a Wi-Fi hotspot called mm_device. It also started a new Bottle-based app. So Bottle is a Python micro framework. So this is a small REST API that's running on the device. So it's a Wi-Fi hotspot with an onboard API. So at this point, when we click next, the app takes us through a wizard that lets us identify our desired Wi-Fi. In other words, what is the Wi-Fi we want the device to connect to for ongoing use? And so once we've collected that data, the app itself will connect to the Wi-Fi endpoint and make a call to that API in order to send over the data. Now, to help you visualize this, I'm going to show you in my phone settings. You can now see that there's an mm_device Wi-Fi hotspot. I'm going to connect to this Wi-Fi hotspot, which means now my network is connected to the actual device. Next, to help you visualize the API call, we're going to use an app that allows you to make RESTful calls. And you can see that we're sending a call to 10.42.0.1. That's the network that's being hosted by the device, to an endpoint /configure. The JSON data that we're sending includes an SSID, a passkey, and the owner. The owner is the ID of the user who's logged into the app and that the device should be associated with. So as soon as we execute this command, you'll see some interesting things that happened on the device. One is it confirms the SSID is valid. In other words, can the device itself see that SSID in the environment? It then connects to that new Wi-Fi using the SSID and passkey that were included in that JSON document. And then once it's connected to the internet through the consumer's Wi-Fi, it reaches out to the cloud backend and updates its own device configuration to now reference the owner who's logged into the app. Okay. Now at this point, you'll notice that the MM_device hotspot goes away and the device puts itself into a normal running mode. In other words, it's now connected to the internet. And you'll see that the flashing blue light will go back to solid white. And so that's an indication to the user that the app or the device is ready to use and now communicating on the back end. So a quick look at messaging. We used Firebase real-time database for messaging. A message being sent from the device to the consumer app is human readable because it's the human that will be reading that. That's an example on the top here of the device sending a message to the user saying, hey, a spray just executed in your backyard. On the bottom, you see an example of a message being sent from the consumer to the device saying refresh config. Since this is machine actionable, these have to be more rigidly defined. The device sends periodic status updates by way of Firestore. On the left is how the update is presented in Firestore. On the right is how that is presented to the user in the app. These status updates can also be used for back office processes, such as alerting staff that maintenance is required. User actions displayed in the app include spraying now, skipping the next spray, doing a water-only spray. For example, if you're doing maintenance on your system and you don't want to spray solution, but you do want to activate every nozzle and be able to check for leaks or issues with nozzles. You can request a status update, and you can also calibrate the device. For example, if you are replacing a scale or some other component, then this is how you would tear or calibrate that individual sensor. From a spray history perspective, you can see 3 examples here. The one on the top didn't spray because it was below a temperature threshold. So notice that in the last 24 hours, it dipped below 50 degrees. That's configurable by the user, so this system is set to spray at or above 50 degrees. The bottom shows that there was rain observed of more than ½ an inch over the last 24 hours, which is why this spray was skipped. The one in the middle, you can see that the temperatures were above the threshold, the rain was below the threshold, and so you can see the individual details from each sensor and how that spray ran in the spray details view on the right. Scheduling, there are 2 types of schedules. You can add a fixed time schedule. So on the left, for example, this is a view from the app. It's showing that every single day of the week, I want to run a spray at 11 o'clock at night. On the right, I'm showing that for every weekday, Monday through Friday, I want to do a relative time spray 15 minutes after sunrise. Obviously, there are a lot of permutations of this before and after sunrise, sunset, dusk, dawn, and so on. So what is the overall business impact of this project? The new smart device makes it possible to collect and use data to forecast customer needs and business operations for a delightful new customer experience at lower costs. Future direction. It's important to accommodate both DIY and managed accounts. Provide free and premium tiers in the app. Leverage growing data to improve forecasting. Use AI to add value to both the customer and the business. And let every customer enjoy their yard to the fullest. If you missed attending this talk at Next, here's a QR code you can scan to get some great resources to help you build whatever comes next for you. And thank you, and post questions in the comments below.